doing section 6.4 of pre-calc, but we're actually doing some physics problems here. So these are not problems that I would specifically ask you to do on a test. This is something you might see later in physics that you're not going to see in my class on a test, but I want to walk you through how it works so that someday when you see it in a physics class, you don't have a panic attack. Okay, so this is example 6. So Hogan, that's me, is holding Fletch, that's my son, in a wagon on a 20-degree incline. So he's in a wagon, and I'm like standing here pushing to stop him from sliding backwards, okay? So I'm pushing to stop him from sliding backwards. So Fletch plus the wagon total weighs 60 pounds. How much force would I need to push, right? I'm pushing directly up the ramp. How much force would I need to push to just keep the wagon still? I'm not trying to move the wagon, I'm trying to keep the wagon still from sliding down, right? Okay, so to do this is going to be one of those projection problems, and I'm going to explain why in a sec. So first thing we know is that the force pushing Fletch downward, right? This force pushing Fletch downward, which I'm going to call F, is the force due to gravity. And because it's pushing, he weighs 60 pounds total with the wagon, that vector is going to be a 0, negative 60. Notice that gravity pushes straight down. It doesn't push down the ramp, it pushes straight down. In fact, this is why inclined planes, right, like this ramp, this is why it's easier to push something up an inclined plane than it would be to just, like, say, carry it up a ladder, right? This is why we use ramps for things. Because essentially, what a ramp is doing is it's decreasing the amount of actual pushing you have to do because you're only pushing against the projection of this weight onto your ramp, right? So that's why a ramp that is less steep is easier to push up than a ramp that is more steep. Because the lower the angle, and obviously my 20 does not look like a 20, but the lower the angle, the less amount of the force projection is actually on you. So I'm going to use this little unit vector r to mean ramp, okay? So here's the idea. When we look at this force, right, the ramp has a direction, right? When we look at this force, what we're really looking at is that it's the part of the force vector, and again, I shouldn't have extended all the way up, it should have gone to the surface. The part of the force vector that I'm concerned about is this part, the part that aligns with the ramp. I'm not worried about the part that is orthogonal to the ramp, right? My problem is this part of the force vector. So essentially, the part of the force that I have to work against is only the part that is pushing in the direction of the ramp. So how much force I need to figure out, that's going to be the magnitude, it's going to be the physical size of how much of F is being projected onto the ramp. Okay, that's how hard I'm going to have to push, is the magnitude of how much of F is being projected onto the ramp. So we need to find the component form for the ramp, and then we're going to be able to use the projection formula. So this is going to be my answer, right? I just have to get there, okay? So let's go over here for a sec. So this ramp, I'm just going to use the unit vector, okay? So I'm going to use r. I'm going to say that r is a unit vector, okay? I'm going to specifically, I'm going to say the magnitude of r is a 1. I'm going to be lazy and use a unit vector. And I know this is 20 degrees. So since r is a unit vector, I know that the y component and the x component, r, must be able to be written as cosine of 20 degrees and sine of 20 degrees, because I lazily chose r to be a unit vector. Because again, I really only care about the direction of r, and the direction of r is up the ramp. So I drew r to be the angle of the ramp, okay? So if I use that projection formula, and you don't have to have this memorized, it's on page 444, but the projection of F, which is the amount of weight, right, that's the weight, onto r, is going to be, and you don't have to have it memorized, you just have to be able to find it on page 444, the r dot f, right, which would normally be u dot v, but I'm using r and f, over the magnitude of r, which I conveniently chose to be a 1, quantity squared, times the r vector, right? So I'm going to go ahead and find those quantities and get once I get this vector in component form, I can find its magnitude pretty easily by using essentially the distance formula. So I'm going to go ahead and do r dot f. Now what I want you to notice is f is 0, negative 60. So it seems to me that r dot f is going to end up being a 0 minus a 60 times the sine of 20 degrees. And I already know that the magnitude of r is a 1, so the magnitude of r squared is still a 1. So it seems to me that this is just a negative 60 times the sine of 20 degrees. And I already know that r is cosine of 20, sine of 20, right? So it seems to me that this projection of the force onto the ramp is a negative 60 sine of 20 degrees, cosine of 20 degrees, comma, a negative 60 sine of 20 degrees, cosine of, another sine of 20 degrees. My bad. That's a sine of 20 degrees. Sorry, screen went blank for a sec. Okay, so I'm going to go ahead and put this in my calculator and store it as A and store it as B. That means that the magnitude of the projection of F onto the ramp, which is the part I care about, that's how hard I physically would have to push, is going to be the square root of the thing I called A and the thing I called B, A squared plus B squared, right? And that's going to tell me how hard I have to push in pounds, right? So if I type those in my calculator, right, I'm going to type in -60 sine of 20 cosine of 20, right? Hit enter and store that as alpha A. Stow alpha A. Sorry. Stow alpha A. There we go. All right. And then I'm going to hit enter, second enter twice. And then I'm just going to change that cosine into a sine using type over and hit enter. And I'm going to stow as alpha B. Sorry, that came out as a T. I meant alpha B. There we go. And so now what I need to type in, right, I have my A and my B. I type in the square root of alpha A squared plus alpha B squared. And I'm going to get that I have to push with 20.521 pounds of force. So 20.521 pounds of force. That's how hard I have to push. So even though I'm pushing something that weighs 60 pounds, I only need to push with 20.512 pounds of force just to keep it stationary. So what I want you to keep in mind is that if I were just holding a 60-pound object and I were trying to keep it stationary just holding it, I'd have to put in 60 pounds of effort to keep it aloft. Because if I'm just fighting gravity, strictly gravity, and I don't have the assistance of an inclined plane, then I have to put in exactly the amount of force that I'm fighting against. That's why inclined planes and other simple machines are able to make life a lot easier, right? It's the same reason that you're able to, let's say, screw something in when you use a screw. The incline on that screw is what makes it easier to screw it in, because you're not actually trying to apply force directly. You're actually using that inclined plane to take advantage of it. It's called mechanical advantage. Anyway, that's it. Some physics for